I came from Poland. My name is Rafał. I'm super happy and excited to be here. It's my first time in India, and so far I really like it. And today I will tell you about caching, and especially about architectural patterns for caching microservices. But first, a few words about myself. So everything was already introduced. I'm an author of the Continuous Delivery with Docker and Jenkins book. I also worked at Google at CERN before, and now I work as a cloud software engineer at Hazelcast. And I'm based in Krakow in Poland. Also a few words about Hazelcast. Hazelcast is a distributed company. It's a distributed company in two meanings. First is distributed because we produce distributed software. But the second meaning is distributed because we all work remotely. So all teams are distributed. We have people all over the world. We have about 40 engineers and 140 people in total. We have three products. We produce open source. We have three products. First one is the most known. It's Hazelcast IMDG, which is, we call it cache on steroids. The second one is Hazelcast Jet. It's a library for big data stream processing. And the third product is Hazelcast Cloud, which is Hazelcast put into cloud version of Hazelcast. The agenda for this talk is very simple. There will be a very short introduction about caching in general, and then we will walk through all architectural patterns that are possible for your microservice system. I would like you to answer yourself two questions during this talk. So first one, which of this pattern do you use in your organization, in your project? Because for sure you use caching and you must use one of these patterns because this list is complete. And the second question you can ask, I would like you to ask yourself is, can I change to any other pattern? Does it make sense to change to any of other pattern for my project? Let's start. So caching in general, everybody uses caching. We do it for mainly two purposes. So first one is the performance. That's the most obvious. So you don't want to make the long-lasting calculation in your backend, or database is slow, whatever. So you use just cached value. So we decrease latency and reduce the load. The second one is maybe a little less obvious. It's for resilience. So you can imagine that you have a system that is down, but you still provide the cached value, and the user may not even know about it. If you can do it or not, that depends on your use case, but sometimes it makes sense. For example, if you are in Amazon and you are in Amazon displaying this recommended items, maybe the old value is still correct. User will not know that your service is down. We are here to talk about how to put cache in microservice system. So that is an example of a microservice system. We have services. Services can have versions. Services, they use each other. They can be written in different programming language. Now, the question is, where is the right place to put your cache? Is it inside each of the microservice? Or is it outside as a separate unit, as a separate cache server? Or maybe it should be in front of a group of servers? And there is no one good answer, and that is what this talk is about. Let's start from the first architectural pattern, which is embedded cache. That is the simplest possible. It looks as follows. A request comes to our system, it goes to the load balancer, and the load balancer forwards this request to one of the application web services. Now the application wants to check in the internal cache, like, do I have this cached value or not? If yes, return the cached value. If not, do some long-lasting business logic and then put it into cache and return the response. This long long-lasting business logic can be anything. It can be a database call, it can be some long-lasting calculation, it can be some call to external service or internal service, anything that is time-consuming. We could implement the embedded cache even ourselves, like in Java we could use a concurrent hash map. Exactly the algorithm I just described, so we get the request, we check if cache contains the request, return if it contains, if not, we do some processing, put the response into cache and return the response. That could be our cache, but please don't do it. Don't do it because Java collection is not a cache, because it has no eviction policies, no max size limit, no statistic, no built-in cache loaders, no expiration time, and no notification mechanism. So we could do way better than just using the standard Java library. For example, we could use some library dedicated to it, like Guava cache is a very, very good in-memory caching. Then we define all these parameters, which are all these functionalities which are missing in Java concurrent hash map, while creating the cache. Another solution is EH cache. And you will find a lot of much more libraries. If you don't use Java, no problem. For any programming language, you will find a library which provides a simple caching. We could even think about not doing all this caching logic, but go one layer higher and put the cache into our application layer, into our framework, like, for example, Spring. So instead of using just library, you can use the whole framework, one annotation in Spring, and every call to this method will first check if the value is cached, then return the cache value. If not, execute find book and slow source method. But be careful, because Spring uses for concurrent hash map by default. So way better is to define your own cache manager and use, for example, Guava. So you get the idea, like embedded cache is just a library inside your application. Now the issue you may have, imagine the following scenario. Like a request comes to the load balancer and it goes to the application on the top. We do this long time processing, put it into cache, return the response. Now the same request comes to the load balancer, but this time it goes to the application at the bottom. We will have to do the processing again, because these caches are completely separate. So the next pattern, it's actually not a different architectural pattern, but a variation, an improvement to the embedded cache. It's embedded distributed cache. It's still the same logic, but this time we'll use a different library. So this time, internally, we will use Hazelcast instead of Guava or instead of EH cache. So the architecture is still the same. However, each cache in each application, they will all together form one caching cluster. So this time, no matter where the calls goes, the cache is one cluster, so the data is shared. Hazelcast is written in Java, so we can embed it natively in Java. If you use other language, you have to find some other library than Hazelcast. It is just a library, so if you use Spring, all you have to define is a different cache manager. This configuration, this is the only thing you have to change in Spring for all your application to use Hazelcast everywhere. You may wonder, like, how it's possible that I deploy my application, it can be deployed anywhere on-premise services, on Kubernetes, or anywhere, and the cache, it's formed together. So what we do is we provide discovery plugins for each environment. So if you use AWS, you just use AWS discovery plugin, and your internal library, your internal cache, they will find other caches in your AWS. The same for Kubernetes and other systems. If you happen to use on-premise services or something that is not supported, we have some more plugins that are like community-based, so people write their own. But if you don't find something that fits you, you can always run Eureka service registry, and then Hazelcast will use Eureka to discover other cache members. We do a lot of blog posting about this discovery plugin. So if you don't know how to configure this, just Google how to use Hazelcast with Eureka, and you will find the answer. So that is our embedded distributed cache. So now let's look at the pros and cons of using embedded cache. So fast. This doesn't work. Okay, the pros and cons. So the good thing about embedded cache is very simple to configure and deploy because it goes together with your application. You have very low latency data access because after all it runs inside the same JVM, inside the same process, and on the same machine. So you couldn't do anything better actually. And you don't need any ops team needed there is no ops effort to maintain this cache. From the downsides, the management is not flexible because it scales up and down together with your application. It's limited to JVM-based applications, and the data is collocated with the application. We covered the first pattern. Let's look now at this next architectural pattern, which is client-server. Client-server is kind of database style. So your application connects to a cache server like the database. So again, the request comes to load balancer, it goes to the application, and application checks in the cache, but to check in the cache, it uses cache client to connect to the cache cluster, cache server. Now, if we compare it to the embedded mode, there are two main differences. First one is that it's separate. That means it's separately managed, which is good and bad things. Bad is that we have to take care of this. We have to have some ops team or some as the previous presentation, some DevOps engineer who will take care of this. In general, like some ops effort. But the good thing is that we can manage it separately, like scale it up. No matter what the application does, we can scale up the server cluster to 10 nodes. If we have more load in the cache server, we can do it 20, whatever you want. But there's also a second difference. And the second difference between this and embedded cache is this part. So this time, we use a connector, a library, cache client library, to connect to cache server. So there is some well-defined protocol between client and server. So you can use the library in any programming language you want. And that is actually a very common strategy, that you have like one cache server, and then all your microservices written in different programming languages, they connect to this cache server. And in this pattern, you can actually use some alternatives to Hazelcast, like the most popular is in web development is Redis. There's a great chance you use Redis or Memcache. Actually, Redis and Memcache, you can use them only in client-server mode because they are written, I think, in C, if I'm not mistaken, and you just cannot embed them into your application. So the only mode they can use them in is client-server. So coming back to our diagram from a moment before, since cache server is can be managed by a separate team, like ops team, we can even move this effort outside our organization and move it into cloud. So cloud is still, in terms of architecture, it's kind of client server. However, it has some different traits. That's why it can be considered as a separate pattern. Because this server now is not managed inside our company, but by a cloud provider. So you don't have to worry about all this organizational stuff. It's done by someone else. Nevertheless, as I mentioned, in terms of architecture, it's kind of similar to client server. So if you, for the cache in the cloud, cache as a service, you have to find your cache in the cloud provider. So Redis offer their Redis Labs. We offer, as a Hazelcast, we offer Hazelcast Cloud. If you are interested in Hazelcast Cloud, you can go to the cloud hazelcast.com webpage, create your free cluster and play with this. Then the configuration in Spring looks as follows. So this time the cache manager is a cache client, and it uses some discovery token and password to connect to your cache cluster in the cloud. Short summary about client server and cloud cache. So good things is that data is separated from applications, and that is actually very, very important for especially big organizations, because they want to keep the data separate from the applications because of the security, because of the also of resilience and so on. So they want to keep it separate. So we, as a Hazelcast, we also have an enterprise version which is dedicated actually for big enterprises, and they actually all of them, they use this client server mode. You have separate management, which is good because, as I said, you can scale it up and do everything you want separately. And it's programming language agnostic, so you can use any programming language you want. From the downsides, it requires some separate ops effort, as we mentioned, but also from the downside, it's higher latency. About this, we didn't speak yet, but imagine now your server is somewhere else. It's not inside your application, so you need to connect to this. So it's important, like, imagine that your client, your application is running in India, but server is in US. It will be super slow. But so it's important to have the same geolocation, but it's not even good enough. I mean, it's the caching is the area of in-memory data computing, which is usually has very, very high requirement in terms of latency. That is why it's even the same geolocation is not enough. We usually want to have the same local network, or at least like not many network hops in between. That is why when we prepare like this Hazelcast Cloud version, you can choose, while creating the cluster, you choose the region, you choose the cloud provider, because if your application is running on AWS, you don't want to have your cache on GCP. But also, what we do is what is called VCP peering, so that your cache will be in the same virtual private network as your application. Because of this reason, because not to have too many network hops. And that is important in terms of cloud, but also if you set up your own cluster server, you have to think about it, where to put it, and for all your applications. If your application is running in multiple regions, then you need multiple cache servers. We are done with the simple caching patterns. Now let's move to something more exotic. So the first two architectural patterns, they may have sounded obvious, because like embedded and client server, it's kind of, you could design it yourself. It's simple. This pattern will be something completely new. So the sidecar caching. This time, this diagram is Kubernetes specific, because the sidecar pattern is mostly seen in the Kubernetes environment. So a few words about Kubernetes is now super hot topic, but maybe a few words if someone didn't hear anything about Kubernetes. So a few words about Kubernetes. So in Kubernetes, a deployment unit is called a pod. And a pod contains usually one container. This is your application running. However, sometimes it can contain, technically it can contain as much containers as you want. And these additional containers, they usually provide some additional functionality. It can be, for example, login agent that will redirect your logs of your application somewhere else. And these additional containers, they are called sidecar containers. So the idea here is to put your cache as a sidecar container, always deployed with your application. Important thing about Kubernetes pod, all containers in one Kubernetes pod, they are always deployed on one physical machine. And that is very important because you can already guess it's because of the latency. So speaking about this diagram, so again, request comes to our system, it goes to Kubernetes service, which is kind of a load balancer in Kubernetes world, and then it goes to one of the Kubernetes pod. It goes to the application container inside that pod, and now the application uses cache client to connect to the cache server, but this cache server happens to be container deployed on the same machine in the same pod. So the application thinks it connects to the server, but actually the server is together with the application. So this solution is kind of a mixture of embedded mode and the client-server mode. It's embedded because you always deploy cache and application on the same physical machine. It uses the resource pool together with your application. It scales up and down together with your application. And you have no problems with discovery because it's always localhost. However, looking from another angle, sidecar cache is more similar to client-server because application can be written in any programming language because it uses cache client after all, cache client library to connect to cache. And there is some kind of isolation between cache data and application. The code, we are already stick to the Spring code, so the configuration would look like this. So we create a client config, so we use client library to connect to the server. We make a configuration static to the static address because we know that it's always deployed on a local host on the default port, so there's no problem with that. So that is our configuration for the application. If you're interested in how it's configured in Kubernetes, so we have this deployment template, and it has two containers. So each pod created from this deployment will have two containers. The first one is our application, so our business logic, and the second one, it will always be the same. It's just the cache server. So short summary in pros of such solution is the configuration is again very simple. It's programming language agnostic. We have low latency again because it's the same machine. It's not the same JVM, but it's still the same machine. So the latency is still okay. And there is some kind of isolation between data and applications. From the downsides, it's limited to container-based environment, not only Kubernetes, but because Sidecar is not only in Kubernetes, but to container-based environments. The management, again, is not flexible because it scales up and down together with the application. And technically, the data is collocated with application pod, so we have it in the same pod. So now we go to the last architectural pattern, which is something slightly different. Because so far, it was always the application that decided to connect to the cache and to decide about all this caching logic. So the application was aware about the caching. This time we will put the cache in front of the application. So it looks as follows. So the request goes to our system. It goes to the load balancer. But this time it's the load balancer or something in front of the load balancer or just after that decides if the request should be cached or not. And if we don't have the cached value, then it goes to the application. So the reverse proxy caching is application does not even know that it's being cached. And actually, the HTTP reverse proxy caching is one of the features of Nginx. So with such a configuration, you can enable this in your Nginx configuration. Good thing is that Nginx, you probably, a lot of you uses it, so it's very mature solution, so you can use it right away in your production. No problem with that. That is this. You can configure much more, but that is the main idea. You specify in which place on the disk the cache should be stored and some timeouts and so on. The problem with such approach with Nginx is that it's limited to HTTP requests, it's not distributed, it's not highly available, and the data is stored on a disk. Which, for some use cases, is good enough, for some not. That is why one of the options is that we use Nginx with some module. There is a module for Redis. There is no module for Hazelcast yet. But anyway, these modules are still like not very mature. So I wouldn't recommend Hazelcast because it does not exist. But even Redis, it's kind of not mature. But another idea is to take this reverse proxy idea and merge the idea with the sidecar pattern. And that's how we come to the reverse proxy sidecar. Again, it's an extension of reverse proxy, but it could be classified as a separate architectural patterns because it's so different. Let's look at the diagram how it looks like. Again, as with the sidecar, we limit ourselves to the Kubernetes environment. And now it works as follows. Request comes to our system. Kubernetes service load balances the request to one of the pods. However, this time in the pod is not the application that receives the request. It's the container with the cache, reverse proxy cache container. And this reverse proxy cache container, it decides, should I return the cached value or maybe forward it to the application. So it passes the request to application only if it cannot find the cached value. And again, application does not even know that the cache exists. And this fact has some good and bad sides. Let's start from the good things about it. You remember we started our presentation with this diagram. This diagram is an example of a simple microservice system. So now there are a lot of microservices that can be written in different programming language, in different version, and so on. Now we can look at the architecture of this and say, and introduce the caching layer. Let's say we would like the caching to these two services. And we don't even need to go into the code of the services. We just specify in a declarative manner that I would like the cache to be applied to these two services. And that's all. So you see the beauty of this. It's like you can measure the performance of your system from outside, not going into each service, and say, okay, we need caching in this part and this part. And we don't change the code, so we don't risk even introducing some bugs into the service. So in Kubernetes, this configuration would look like this. This time we will have 3 containers. I will explain in a moment why. Let's maybe start from the 2 containers at the bottom. The last one is the application. We already know it. That's our business logic. This doesn't change. Caching proxy is this container that will receive the requests and pass it to application or not, depending if it finds the cached value. We also need an init container, which is init networking. Init container is a container that is just run before we start our containers in Kubernetes. What it will do? So we need to change the networking inside our Kubernetes pod, because this time we don't want the application. Normally the application receives the request, because this application that has this port open. But we need to change it. So we want to change it in a way that each request coming from external, from outside the pod, will go not to the application but to our caching proxy. So this init networking will be just a simple script that will change our IP tables inside our Kubernetes pod of how the traffic is routed. This is like if you would like to configure yourself, you can use it this way. However, like if you look at this diagram, it may come to your mind the Istio service mesh is this kind of thinking, and Istio is actually planning to introduce caching. They are already working on the implementation for caching, like to introduce caching using like Istio way, so declarative way. So you just change the Istio configuration to introduce caching to some of your services. But I said it also has bad sides, like such approach. In general, reverse proxy has some bad sides. Because it may sound like a great idea, but there is one thing that becomes way more difficult using reverse proxy pattern. And that one thing is cache invalidation. So if you look anywhere on the internet, what causes the most issues with the caching, everyone will tell you the same. It's the cache invalidation, meaning when to decide that the cached value is already stale. If you cache the database, so how do you know that the value in the database has changed? And I should not take it from cache, but go directly to the database. So if application is aware of caching, we could, in Spring, for example, create a method, okay, if some business logic happens, then invalidate my cache. So the business logic can decide what happens with the cache. However, if we use reverse proxy, then we are limited to some standard HTTP things like timeouts, ETAG. Generally, it will be based on some timeouts. Short summary about reverse proxy and reverse proxy sidecar patterns. Good things is the main reason for using this is configuration based, so no need to change your applications. It's obviously programming language agnostic. It's everything agnostic. It does not even touch your code. And it's very consistent with the container and microservice world, cloud native, all what happens right now. This pattern is very consistent. From the downsides, we mentioned cache invalidation becomes very difficult. But there's also, there is no mature solution yet. So it will become you will hear about it more and more, I think, in a year and two. But as for now, we in Hazelcast, we created a prototype, like a proof of concept. So you can use it. I will share a link, but don't use it in production. And as I said, like Istio is working really heavily on that. So soon you will see a solution that you can use in your production. And obviously it's protocol based. So usually in today's world will be HTTP based. I'm not sure if it is such a big drawback because we are already HTTP centric so much that it's not an issue. So this was the last caching pattern. So as a short summary, I know there are a lot of them, so I would like to make a structure out of it and help you make decision which one to choose. So I created like a short decision, what is called decision tree, how to choose the right caching for you. So the first question I would ask, do I need my application to be aware of the cache? If no, then is it container-based? If no, then just use reverse proxy from Nginx. That is a major solution, you can use it. If it's container-based, then you can use reverse proxy sidecar as soon as it's available. But it will be. Trust me, it's coming. If your application needs to be aware about caching, then another question is, do I have a lot of data or some security restrictions? If no, then does it need to be language agnostic or is it based on containers? If no, just use simple, well-known embedded distributed cache. a lot of people use it, and it's actually good especially for small projects and for just caching. It's good. However, if you use containers or you want to have language agnostic, Sidecar is the way to go. Now, if you work in a big organization and you have a lot of data and some security restriction, then the last question you need to ask yourself, is my infrastructure a cloud? If no, then use client server, set up your server. If yes, then use the cloud version of a cache provider. So as the last slide, I prepared like a few resources. So the first one is the blog post about setting up the Hazelcast as a sidecar container. The second one is I mentioned we prepared like a proof of concept, a prototype of the HTTP reverse proxy sidecar, so you can play with this. Don't use it on production, because it's just a proof of concept. The third is about caching in general. It is a very good blog post about, in general, caching patterns that you should follow. And the last one is a very good video talk from Nginx about their solution, the HTTP reverse proxy. I really recommend watching this. Thank you all. It was a pleasure to speak here. Do we have time for questions? Yes, so do you have any questions?
Hi there. Thank you very much for walking us through these topics. So I have two questions. First question is, this is on the embedded distributed technique for caching. Since it's done on the application level, I think it is either stored in memory or in disk, the caching. So do you think we can fine-tune the garbage collection to have a lot of caching happening just on the application side so that the performance is good?
So if I understand, the question was, if you use embedded cache, then you have obviously garbage collecting about caching, like cache eviction, and is the performance good?
Yeah, would it be acceptable to have the garbage collection fine-tuned to have the application perform good with the embedded distributed technique option?
Yeah, I think this question, it goes not only to embedded cache actually, because even if you have cache server, you have you have the same problem. I mean, the same. Hazelcast is still written in Java, so it will still have garbage collecting. But other solutions, you will still have this cache eviction. That is why I think it's a general question: is it a problem, a performance problem? I would say you have to think about it. I mean, if you really strive for performance in any caching solution, in any architectural patterns, then you have to think about the memory. Think about memory, it means like how to set up the cache eviction policy. Where should be evicted? You can choose many of them. It can be based on timeout, it can be based on the last one used, and so on. But it also means to set up the reasonable amount of memory for your caching. Because if you set it too low, then you will have a lot of eviction. Obviously, it's simpler said than done, because usually you can do it. I mean, you can measure this and everything, but suddenly there is a peak in your system, yeah? The performance, I don't know, there's an event, DevOps, India, and everybody is tweeting about it. So it will grow up your cache. That is why I think for this solution, the client cache would be better, and then you can use auto-scaling for your cache server. So your cache server will scale up. For example, you can start from 3 nodes of cache, each having, let's say, 1 gigabyte of memory. And then if you could set up auto-scaling, then if the eviction rate is too high, then it will create all of a sudden like 10 nodes. and that will probably solve most of the performance problems. So in this case, like it's easier, I think, with client server. With the application, it's the same, but it scales together. You can use auto-scaling, but it will scale up and down together with your application.
Thank you. The second question is on the load balancer caching. So does it also include the riverbed caching, or is that a separate topic?
Again?
So does it also include the riverbed caching? We have riverbeds, right, for caching each and every
I didn't get the second term. Rivers.
Riverbed.
Riverback or?
Riverbed.
I didn't get it. Like riverback.
that comes in the network side, but I'm just wondering whether the load balancer also includes that stuff as well.
Okay. So okay. So reverse-based caching, like, does once again, could you repeat?
When a user hits an application call, so that would go through the riverbed as well before it hits the application.
Yes.
So I'm not sure whether it would hit the riverbed before the load balancer or after the load balancer.
So in terms of if you Nginx, use Nginx, it can go together with the load balancer. You can configure Nginx as a load balancer and as a cache together. Or you can set it up, actually better, I think, before load balancer. But if you use like this sidecar, then it's always before each of the replica of your application.
Thank you.
Okay, thank you.
I have a question on sidecar and reverse proxy sidecar. Have you considered writing a CRD, a custom resource definition, to embed the business logic, like
Sorry,
cache invalidation?
where are you? I can. Okay, so sorry. Yes. So yeah, a question about sidecar. Yeah, can you repeat again?
Yeah. So, so when we use a sidecar or a reverse proxy sidecar pattern, when I write the deployment and add the Hazel cache as a separate sidecar container, so have you considered writing a custom resource definition to embed the business logic, like cache invalidation, so that I can use a Hazel cache deployment resource instead of a deployment?
So once again, the question was how to set it up.
Oh no, I'm asking, have you considered writing a Kubernetes custom resource to embed the pattern that you are describing?
So once again, the question was how to use. I didn't get the question. Sorry. Can you try to rephrase it?
Oh, can we try to write the sidecar cache and reverse proxy sidecar cache as a Kubernetes custom resource definition?
With the can we define with the Google custom?
Kubernetes custom resource definition.
You mean like you could actually do it this way, but then you have to define your own definition, and then I think you could do it. We actually never did it, but I think it should be possible to specify your customer resource definition as your application with the cache and do it all together. I think it's possible, but we actually never did it. We did custom resource definition like for setting up the Hazelcast, using Hazelcast operator to set it up on Kubernetes. So we used but to setting up the Hazelcast server on Kubernetes, but it's still client server mode. We never did it for sidecar. When I think about it, you could prepare your custom resource definition, yes. But I would need to, try and code it. Then maybe I would have more feedback on that. Would it make sense? Yeah.
Thank you.
So that's it for this question and round. We are up for the next talk. So thank you, Rafal, for this talk. Let's have a big round of applause for Rafal.
Thank you.